Welcome to our YouTube channel. Information Ether. Is it conceivable to teleport? Imagine a baseball transforming into a radio wave, passing through walls and around corners, only to rematerialize as the same baseball. Surprisingly, the principles of quantum mechanics suggest this might be possible, albeit with a significant caveat. The actual baseball couldn't be transmitted via radio waves. However, the complete information defining it could. In the quantum realm, elementary particles like atoms and electrons are characterized by a set of specific properties, such as their position, momentum, and intrinsic spin. The combination of these property values defines the particle's quantum state, its unique identity. If two electrons possess identical quantum states, they are indistinguishable. Extending this, our baseball can be seen as defined by the collective quantum state of all its constituent atoms. Now, consider if this quantum state information could be measured in one location, say Boston, and then transmitted across the globe. In another location, like Bangalore, atoms of the same elements could have this information imprinted upon them and be precisely arranged to reconstruct the exact same baseball. Here's the challenge: measuring quantum states isn't straightforward. The Heisenberg uncertainty principle in quantum physics tells us that we cannot simultaneously know both the exact position and momentum of a particle. The most direct way to measure an electron's position involves bouncing a photon off it and observing the scattered light. However, this interaction inevitably alters the electron's momentum in an unpredictable way, erasing any prior knowledge of it. In essence, quantum information is delicate, the act of measuring it changes it. So, how can we transmit something we can't fully measure without altering it? The key lies in the peculiar phenomenon of quantum entanglement. This long-standing enigma in quantum physics, still not fully understood, involves linking the quantum properties of two particles, like the spin of two electrons, in a way that creates an instantaneous connection across any distance. If we measure the spin of one entangled electron, we instantly know the spin of the other, regardless of the separation between them, be it a mile or a light year. It appears that information about the first electron's quantum state, a unit of quantum information called a qubit, influences its entangled partner without any transfer through the intervening space. Einstein famously referred to this as spooky action at a distance. While entanglement seems to offer a way to instantaneously transfer a qubit between two particles, there's a crucial limitation. The entanglement must first be established locally, meaning the two particles need to interact in close proximity before one is moved to a distant location. By itself, quantum entanglement isn't teleportation. To achieve teleportation, we need an additional piece, a classical digital message to interpret the received qubit. This message consists of classical bits of information obtained by measuring the first particle. These digital bits must be transmitted through conventional channels limited by the speed of light, such as radio waves, microwaves, or fiber optics. Crucially, the act of measuring the first particle to obtain this digital message destroys its original quantum information. This implies that for the baseball to be teleported from Boston to Bangalore, the original baseball in Boston must cease to exist. Therefore, thanks to the uncertainty principle, quantum teleportation transfers the information defining the baseball between two locations without ever creating a duplicate. In principle, this opens the door to teleporting objects, even people. However, our current capabilities make it seem highly improbable to measure the quantum states of the countless atoms in macroscopic objects and then perfectly reconstruct them elsewhere. The complexity and energy requirements of such a task are astronomical. Currently, we can reliably teleport single electrons and atoms, a feat that holds promise for ultra-secure data encryption in future quantum computers. The philosophical implications of quantum teleportation are profound. A teleported object doesn't simply move through space as physical matter, nor is it just the transmission of abstract information. It seems to be a blend of both. Quantum physics presents a novel perspective. All matter in our universe can be viewed as collections of fragile information, and quantum teleportation unveils new ways to interact with this fragility. And let's not forget, never say never. Just over a century ago, our understanding of electron behavior at the atomic level was just emerging. Now, we can reliably teleport them across a room. Imagine the technological mastery of such phenomena we might achieve in 1,000, or even 10,000 years. Only time and the vastness of space will ultimately reveal the possibilities. Thank you for watching. Don't forget to like, subscribe, and share this video.